In the last lecture, we discussed an experimental procedure called titration and saw how this procedure can be used to determine the concentration of an unknown acid or base. In performing these titrations, we utilized something called an indicator to let us know when we had reached the equivalence point of the titration, where we had added just enough base to just neutralize the acid or vice versa. At the equivalence point, the indicator underwent a dramatic color change. For example, when we titrated a solution of hydrochloric acid with sodium hydroxide using phenolphthalein as our indicator, the solution underwent an immediate color change from colorless to pink with the addition of just one additional drop of base. And when we added just one more drop of acid, the solution immediately changes back to being completely colorless, as we saw in the last lecture. When students first do titrations, indeed, when I did my first titration, what is always very impressive is the remarkable sensitivity these indicators seem to have. Just the smallest drop of acid or base produces an abrupt change in color. How does this happen? I mean, indicators almost appear to have some magical property. I mean, how can they be so sensitive? Why doesn't the color change gradually? You have the impression that these indicator substances must be pretty special chemicals to be able to change color so dramatically with the addition of only one drop of acid or base. What kind of unusual chemical structure could these substances have that allows them to do what they do? When I found out the answer, I was actually kind of disappointed because indicators are really not all that unusual. That's why there's so many of them. The color change occurs so rapidly and so dramatically, not because of some highly unusual property of the indicator, but because of the way water behaves near the equivalence point of a titration. Let's pretend we were going to do a titration of a strong acid like HCl with a strong base. Let's say NaOH. Let's suppose, to keep the math simple, that we started with 25 milliliters of 0.10 molar HCl and titrated it with 0.10 molar NaOH. It's a bit tedious, but not too difficult, to calculate what the pH of the solution would be after the addition of specified amounts of the sodium hydroxide solution. I've done that for you, and here are the results. The initial amount of acid that I'm going to use is 25 milliliters of 0.1 molar HCl. And I'm going to add to this 0.1 molar NaOH. And what I'm going to do is I'm going to present to you a data table that will tell us what the pH of the solution is after I add various amounts of sodium hydroxide. Now, going through this table may not be the most exciting thing that we've done or will do, but I want to take time to go over this table carefully because there's some very, very important principles lying inside the data that we're going to see in this table. Okay, when I first start, I have this solution of hydrochloric acid. I haven't added any base whatsoever to it. So the first line says, when I have added 0.00 milliliters of the 10th molar sodium hydroxide, the pH of the solution is 1. That makes all the sense in the world. I started out with a 10th molar solution of hydrochloric acid. A 10th molar solution of hydrochloric acid will have a concentration of hydrogen ion of 10th molar because hydrochloric acid is completely ionized. If the concentration of hydrogen ion is 10th molar, or 10 to the minus first molar, we know that the initial pH of our starting solution of hydrochloric acid is going to be 1. That calculation we all could have done. Okay, now I'm going to add 5 milliliters of 10th molar sodium hydroxide. It turns out that, as we would expect, that will raise the pH of the solution. I'm adding a base, so the pH should go up. And after adding 5 milliliters of sodium hydroxide, the pH is equal to 1.18. So it's risen by about 0.18 pH units. I'll add another 5 milliliters of NaOH. Now the total volume of NaOH that I've added is 10 milliliters. And the pH of the solution at this point will have risen to 1.38. Another 5 milliliters of NaOH, and now the pH is up to 1.60. Another 5 milliliters of NaOH for a total of 20, and the pH has now risen to 1.95. So you notice that the first 20 milliliters of base that I have added has managed to increase the pH of the solution from an initial value of 1 to a value of 1.95. Now I am going to add the base 1 milliliter at a time. If I add 1 more milliliter of base, total volume now 21 milliliters. This raises the pH from 1.95 to 2.06. Another milliliter of base raises the pH to 2.19. Yet another milliliter, and it's up to 2.38. Another milliliter, 24 in all, and now it's up to 2.69. Now watch carefully. Now I'm only going to add half a milliliter of base. Another half milliliter of base to give me a total of 24.5 milliliters raises the pH to a value of 3, and the next half milliliter of base raises the pH from 3 all the way up to 7. Now I am going to actually go past the equivalence point. The solution is now neutral. I've neutralized all the acid, but now I'm going to add more base. So I'll have an excess of sodium hydroxide, and the pH of the solution should now be greater than 7. If I add another half milliliter of base just past the equivalence point, the pH jumps from 7 to 10.96. The next half milliliter of base raises it to 11.29. Now I will add 1 milliliter at a time. The next full milliliter of base raises it to 11.59. The next milliliter to 11.75. The next milliliter, 11.87. The next milliliter, giving me a 30 milliliters in all, 11.96. And I'm going to add 5 milliliters of base at a time. The next 5 milliliters of base, 35 in all, raises the pH to 12.22. Another 5 milliliters, 40 in all, 12.36. And the final 10 milliliters, 50 milliliters of base altogether, 12.52. So what we notice is that at the beginning of a titration, in fact, well into the titration, the addition of base only raises the pH of the solution by a moderate amount. In our example, the addition of the first 24.5 milliliters of base only changed the pH of the solution from 1 to 3. But when we added only 1/2 of 1 milliliter more of base, the pH changed from 3 all the way up to 7. The last half milliliter of base added near the equivalence point changed the pH more than was accomplished by adding the first 24.5 milliliters of base. And right after the equivalence point, the pH continued to rise rapidly. The first half milliliter of base added after the equivalence point changed the pH from 7 to 10.96, almost 11. But the next 24.5 milliliters of base only managed to change the pH from around 11 to just under 13. We can graph these results to obtain what is called a titration curve. The titration curve for titrating 10th molar HCl with 10th molar sodium hydroxide would look like this. Although we have prepared this curve for the specific example of titrating 10th molar HCl with 10th molar NaOH, its shape nicely reflects what happens when you titrate any strong acid with any strong base. Well, okay, sulfuric acid gets more complicated because its formula is H2SO4, so it has two hydrogens to neutralize. But neglecting this one guy, this curve is typical of all other strong acid, strong base titrations. And the striking thing about these curves is how rapidly the pH of the solution changes right around the equivalence point. The addition of just a small amount of acid or base, literally one drop, produces a huge change in the pH of the solution. And this explains why indicators change color so dramatically around the equivalence point. Our initial definition of an indicator was that it was a substance that was one color in an acidic solution and another color in a basic solution. Now we are ready to present a more accurate definition of an acid-base indicator. An acid-base indicator is a weak acid or base whose molecular form is one color while its ionic form is another. Let's consider something like phenolphthalein. Its actual structure isn't important, so we'll just represent it with the molecular formula HP. Since it is a weak acid, we know that it ionizes to a small extent to form H positive and P minus. The HP molecules are colorless, but the P minus ions are red. But other than this different color thing, phenolphthalein really isn't any different than any other weak acid that we've talked about. It just ionizes like our classic example, acetic acid. And like acetic acid, phenolphthalein has an ionization constant. Using the rules we've learned for writing equilibrium constants, we know that Ka for phenolphthalein would just equal the concentration of hydrogen ion times the concentration of the anion from the acid, which we have designated as P minus, divided by the concentration of the phenolphthalein molecules, for which we have used the symbol HP. And as is true for all weak acids, Ka has some numerical value. For acetic acid, you may remember that the value of the ionization constant was 1.8 times 10 to the minus fifth. It turns out that for phenolphthalein, the value of its ionization constant happens to be very close to 10 to the minus ninth. Now let's rearrange that expression a bit. This expression can be algebraically rearranged and written as the concentration of the HP molecules divided by the concentration of the P minus ions equals the concentration of hydrogen ion divided by 10 to the minus ninth. Now this is slightly subtle and not of critical importance, so if you don't follow the mathematical logic perfectly, don't be too concerned. If you study the rearranged expression, it says that the ratio of HP, the molecular form of the indicator, which is colorless, to P minus, the phenolphthalein ion, for want of a better term, the red form of phenolphthalein, is equal to the concentration of hydrogen ion in the solution divided by 10 to the minus ninth, which is the ionization constant Ka for phenolphthalein. Study that for a few moments if you aren't following this. Forget about the 10 to the minus ninth for a moment. What this mathematical expression tells us is that the ratio of the two forms of the indicator, the colorless form HP and the red form P minus, depends on the hydrogen ion concentration in the solution. If the concentration of hydrogen ion changes dramatically, then the ratio of the two forms of the indicator also changes dramatically. And that explains why the color changes so abruptly at the equivalence point of the titration. There's nothing really special and certainly nothing magical about indicators, other than the fact that their molecular form and ionic form have different colors. They are just weak acids, just like any other weak acid. acetic acid would make a fine indicator, except for the fact that acetic acid molecules and acetate ions are both colorless, so there's nothing to see. And this leads us to a couple of additional things that are good to know about acid-base indicators. As was mentioned before, there are many different indicators. They differ from each other in two important ways. First, as you might expect, they have a wide range of colors. Phenolphthalein is probably a popular indicator for high school titration labs, simply because the change from colorless to pink is so easy to see. The second difference is a bit more subtle. We said that acid-base indicators were weak acids or bases, and like all weak acids or bases, they have an ionization constant Ka, if we limit our discussion to weak acids, which is fine for our purposes. It turns out that a given indicator changes color, so to speak, at a pH value that depends on its ionization constant. I don't really care to go into the proof of this. You may want to try and figure out why this is true on your own. Phenolphthalein, which has a Ka of about 10 to the minus 9th, will change from colorless to red at a pH of about 9, which you probably notice is the negative of the exponent on the value for its ionization constant. If an indicator has a Ka equal to 10 to the minus 7th, then it will change from one color to another at a pH of 7. And if Ka were equal to 10 to the minus 4th, then the indicator would change color when the solution was still fairly acidic, when the pH of the solution we were titrating had a value of 4. I mean, of course, real Kas aren't even powers of 10, but that doesn't really matter. If we know the value for the Ka of an indicator, we know the pH at which it will change color. If you are very good mathematically and understand this real well, you may have already deduced that a weak acid indicator will change color when the pH of the solution into which it is placed equals pKa for the indicator, that is minus the common logarithm of Ka. Well, technically it doesn't change color immediately when the solution reaches that pH value. An indicator actually changes color, quote, gradually around this pH. We usually specify a pH range over which this color change occurs. But because the pH of solutions tend to change so rapidly near the equivalence point of a titration, the color change typically occurs very abruptly, as we've seen. Essentially, we just fly right through the pH range at which the indicator changes color. But as I said, understanding all of this isn't critical. What is more important is just that you understand that there are many different acid-base indicators of many different colors, and that they change color at different pH values. Or more correctly, they change color over a small pH range centered at the pKa of the indicator. Here is a list of some of the more common acid-base indicators and the pH values at which they undergo their color change. You can find much more extensive lists in many textbooks and on the web. These are just a few examples. Let's start with an indicator that actually changes color when the solution into which it is placed is still pretty acidic. Thymol blue changes from red to yellow at a pH range of about 1.2 to 2.8. Methyl yellow changes from red to yellow over a pH range of about 2.9 to 4. Bromethymol blue changes from yellow to blue violet from around 3 to 4.6. Methyl red from red to yellow from 4.4 to 6.2. Phenol red from yellow to red from 6.4 to 8. Phenolphthalein from colorless to red from around 8 to 10. Alizarin yellow from yellow to lilac from about 10 to 12. And finally, nitramine from colorless to orange-brown from around 11 to 13. Now, there's no reason to remember these, but this brief list shows us that we actually have quite a choice of indicators to use for any titration we might be doing. So does it make any difference which one we choose? The answer actually is, it depends. Depends on what? It depends on the titration you're doing. Let's go back to our titration curve for titrating hydrochloric acid, HCl, with sodium hydroxide. When we look at this curve, we notice that there is a huge change in the pH of the solution right around the equivalence point. The addition of just a very small amount of base causes the pH to jump from perhaps 4 to 10. This means that, we really could use any indicator whose color change occurred somewhere in this pH range. Oh, okay, I guess theoretically, since the pH of the solution at the equivalence point was 7, the best indicator to use would be one that changed color at a pH of 7. But for practical purposes, the pH changes so rapidly, and since we can't add anything less than 1 drop of acid or base, phenolphthalein will do just fine. So then, what's the point of having all these other acid-base indicators? Good question. Glad you asked. Thanks. Not all acid-base titrations end up with their equivalence point occurring at a pH of 7. That's the case when you titrate a strong acid with a strong base. But many titrations do not involve a strong acid and a strong base. We have already learned that most acids are weak acids. There are only 6 common strong acids. So what happens if you titrate a weak acid with a strong base? Well, in these cases, when you reach the equivalence point where you have added the same number of moles of base as you had acid to begin with, the pH of the solution is not equal to 7. In fact, it will be somewhat greater than 7. And how much greater depends on the ionization constant of the weak acid that you are titrating. The weaker the acid, the higher the pH will be at the equivalence point. We're not going to explain why this is the case, but there is a very silly, unscientific way to remember this. Pretend you are titrating a weak acid with a strong base. You imagine them talking. One says, "Me, strong base." The other says, "Me, weak acid." Since strong will predominate over weak, the solution at the equivalence point of a weak acid strong base titration will actually be somewhat basic. And the reverse is actually true as well, although we don't run into it as often. If you were to titrate a weak base like ammonia, NH3, with a strong acid like HCl, then we have me, strong acid, me, weak base. And the strong will dominate the weak, so to speak, meaning that at the equivalence point, the solution will actually still be slightly acidic. We can see this more clearly by looking at the titration curve for 10th molar acetic acid, HC2H3O2, a weak acid, being titrated with 10th molar sodium hydroxide, NaOH, a strong base. But before we do that, I'd like to ask you what I consider to be a very interesting question. Suppose you wanted to neutralize 1 mole of a strong acid like HCl. How many moles of a strong base like NaOH would it take? As we discussed, HCl and NaOH react in a 1-to-1 mole ratio. So 1 mole of HCl would just require 1 mole of NaOH. But that wasn't the interesting question. Let's suppose you wanted to neutralize 1 mole of a weak acid, like acetic acid, HC2H3O2. You know and I know that acetic acid is only slightly ionized into hydrogen ions and acetate ions, which means that a solution of acetic acid will only contain a relatively small amount of hydrogen ion. So will it take more, less, or the same amount of base to reach the equivalence point? Pause the video and think about this. I'll give you a hint if you'd like one. If you don't want a hint, pause the video right now and try to answer the question. Okay, I assume you either answered the question or now you want to see the hint. Here is the hint. Think about what happens when you add the base to the acid and see how Le Chatelier's principle would apply here. The correct answer is that it takes just as much base to neutralize 1 mole of a weak acid as it takes to neutralize 1 mole of a strong acid. Students are often answer this incorrectly, even many who have an excellent understanding of what is going on. And that's very understandable. They reason that since weak acids are only slightly ionized, there is very little hydrogen ion in a solution of something like acetic acid. And since there is very little hydrogen ion to be neutralized, it's not going to take much base to do it. But the catch is that, according to Le Chatelier's principle, as you neutralize the hydrogen ion that is present in the solution, more of the acid ionizes to try and replace this hydrogen ion. Essentially, you add some base. It swims over and gobbles up all the hydrogen ion that's in the solution, since that wasn't very much. But as soon as you remove this hydrogen ion, some acetic acid molecules ionize to try and replace it. Remember, the system always tries to do the opposite of what you did to it. So you neutralize the new hydrogen ion that's been created by adding a little more base. But then even more molecules of acetic acid dissociate and try and replace it. This will form a little hydrogen ion and also more acetate ion. So you neutralize the new hydrogen ion that's just been created. No use. More acid just ionizes to replace it, producing a little bit of new hydrogen ion and even more acetate ion. You are fighting a losing battle, so to speak. No matter how much hydrogen ion you neutralize, as long as there are any acetic acid molecules remaining, they are going to keep ionizing to replace what you have neutralized. You are not going to be successful until you have, in essence, added as many moles of NaOH as there were acetic acid molecules to begin with. So it takes just as much base to neutralize a given amount of weak acid as it does to neutralize the same amount of a strong acid. Now let's take a look at the titration curve for 10th molar acetic acid being neutralized by 10th molar sodium hydroxide. When you compare this titration curve with the one for a strong acid, strong base titration, the one we talked about earlier, there are a few important differences. First, you notice that the pH at the beginning of the titration is higher, somewhat larger than 2. 2.88 actually, if you do the calculation. This is simply due to the fact that a weak acid like acetic acid is only slightly ionized. So the concentration of hydrogen ion at the start of the titration isn't as high as it would be if you were titrating a strong acid that was 100% ionized. Like the strong acid, strong base curve, the pH of the solution does not rise very rapidly at the beginning of the titration. There are some subtle differences in the way the beginning of the curve slopes, but discussing the reasons for these differences gets pretty involved and doesn't really matter for what we're discussing today. The next major difference that you should make note of is that there isn't quite as dramatic a jump in pH around the equivalence point. Again, the reason for this is somewhat complex. But the most important difference to note is that at the equivalence point of the titration, which is at the middle of the almost vertical part of the curve, it does not occur at a pH of 7, but rather at a value somewhat higher than 7, our me strong base, me weak acid thing. So if I wanted to select an appropriate indicator for this kind of titration, we would have to select one that would change color somewhere in the vertical portion of this curve. Phenolphthalein, which changes color at a pH of about 9, would be very good. Thymol blue, which changes color closer to a pH of 2, would be a terrible choice. In fact, it would have changed color, so to speak, before we even began the titration, since the pH of our starting solution was greater than 2. As you might surmise, there is a lot more that can be said about acid-base systems. But, we have to stop somewhere, so we'll stop here. Unless you are enrolled in an advanced course, it is doubtful that you will be expected to go past this point. And if you do, your sound foundation will hopefully allow you to easily understand whatever new information is presented. In the next couple of lectures, we're going to take a look at one additional type of important equilibrium, the kinds of equilibria that exist in solutions of slightly soluble ionic solids.